Hi, everybody. We're going to keep exploring memorization. I'm a little bit cozy today. It's December here in Berlin. So let's get cozy and explore what happens when you have a bigger model than you have data. Let's find out. So, when I talk about overparameterization, or when we talk about overparameterization, what we're talking about is the massive model growth size. And we can call a model overparameterized when it has more parameters than it has data. So just to get an idea of what do we mean of this model growth that's happened in recent years, here I have just a very small visual comparison between the openly, or not openly released, but between the released OpenAI models. So comparing here on with one, GPT-2, GPT-3, and the presumed, it's not fully known, but the presumed parameter size of GPT-4. And we can see that we're going from GPT-1 of 117 million parameters to GPT-4 supposedly 1.7 trillion. So we have a huge growth in a fairly short period of time. And all of these models were considered overparameterized compared to their data set. What does that actually mean, though? What is a parameter? Well, let's take a look in case you're not familiar. Neural network has these neurons, or as I like to call them, nodes, because really what we're computing on is a graph, and we have nodes and edges. And one reason why we think about it like a graph is because it allows us to do parallel computation. And so neuron is also just a little bit of an outdated word. We're not building a brain, we're building a computing system. And so we have these edges, which are essentially little arrows, directional arrows between different nodes. We have the nodes, usually you've seen them sitting in layers, so they sit in layers. And then data or the processing flows between the incoming nodes and then through their edges to the next layer of nodes end, until at the end we get some sort of final matrices or final decision representation that allows us to make a prediction or to generate output and continue. And so in these neurons, we have what's called a bias parameter. In the edges, we have what's called a weight parameter. You might have heard already about weights and biases. This is what we're talking about. Usually there's some sort of function inside the node that allows you to compute some sort of value, often a sum, but could be anything. And that combines the incoming weights with their incoming data, more on that in a minute, with the bias. And then the output of that function gets put through a so-called activation function. So you might have heard of ReLU activation or a sigmoid type of activation. So there's going to be some sort of activation function. And basically what that means, without getting into too much of the math, is you take those sum that you just calculated or whatever you just calculated, and then you essentially put it on a scale, most likely, where it could be either on or off if you want it to be really explicit. So is it on? Is the node on or off? Or how on or off is the node? So maybe a scale from 0 to 1 or a scale from -1 to 1. And so this is some sort of float at the end usually, and then that gets combined with the weight on the next edge and sent to the next series of nodes. And these are all connected. So when we have what are called fully connected layers, that means that every node in one layer connects to every node in the next layer. Now, not every neural network architecture or deep learning architecture has this set up. So there might be dropout layers where there's less neurons or nodes and some of them just get removed. There might be not fully connected layers where we have some sort of pooling or where we have other types of architectures. And this again goes back to deep learning is really all about the architecture more than it is about a particular algorithm. Although, of course, you get to choose things like the activation function and some other things that might help your network learn better. And so usually we have all of these nodes aligned in an input layer, and then we have what are called the hidden layers, which is in the middle, and then we have, one or a few output layers that essentially are trying to take the deeper representation from those hidden layers and come back to some sort of smaller decision space. And so this is kind of what we mean when we say parameters. So each of these nodes we can think of has, for each of their edges, for each of the little arrows going out, there's the weight parameter. Inside they have the bias parameter, and this is their parameters. So when you think about 1.7 trillion parameters, there is a lot of nodes. There's a lot of nodes and there's a lot of layers, and there's some special layers that may use also additional parameters, but we don't need to get into those details. Basically, what I want you to take away is that when you have these overparameterized, you have more parameters than training examples. And if you have a mathematical or statistical brain, you might be thinking, well, one way to learn would be that we just save the data in the parameters, because technically we have more parameters than we have data. We could just say, oversimplifying, but we could just say, this node, your job is to learn training example A. This node, your job is to learn training example B. And we could encode essentially all of the information from the training examples directly in the network. Now, obviously, that's not what we're trying to do when we're trying to do machine learning. We're trying to actually learn. But what we unfortunately found out is maybe some of what we're learning is this encoding or this memorization of the information from the training examples directly into these overparameterized models. Xiwan Zhang took a look at this by completely randomizing computer vision labels, and were able to train a normal deep CNN network, a computer vision network that completely scored well on randomized examples. So a cat was a swan, and then, the next cat was a boat, and they were able to show that the neural network perfectly scored on the training data set, and of course performed very, very poorly on any real data set. But this was a big aha and led to a bunch of research around, do we actually know what's happening in deep learning? And do we know whether memorization is fully happening as part of this training? And so Zhang Bengio et al., a group of folks in 2020, released this paper, Identity Crisis, where essentially they wanted to train a computer vision network to learn the identity function. And if you're familiar with linear algebra, you already know this, but a quick summary. When we have an identity matrix, we take a matrix in, or we take some sort of n-dimensional representation in, and then we want to return the same thing. So for computer vision, they wanted to take an image in, and they wanted to put the same image out. And how they did this was they trained first just on the same image over and over and over again. And here we can see the results of doing that when they then showed other new inputs. So what you want to see across this top layer of this image is we have the input that was put in, and then we want to see the output of different depth of deep learning networks. So we have a one-layer network. Well, the one-layer network performed really well. It learned the identity function. The three-layer network learned pretty well. The 5-layer network, we can see as we go through, does the image look like the top image? And then as we get kind of to the 9 to 14, 15 layer, we see that it starts to learn something different, edges. Okay, that's it. That was an interesting outcome, unexpected. And then as we get to the deeper layers, we see that it has actually simply memorized the 7. And in parallel work, and actually work before this work, another group of computer vision researchers were looking also at this problem. And they found that when they were looking at the CNN architecture and the pooling layers, so this is layers that essentially try to compress the incoming information into different sections, and then learn further. That's a very high level. Probably somebody in computer vision can comment and describe it even better in the comments. But we're essentially trying to compress and downsample, we could also call it, which is in their paper title, sections of the image. And what they found, interestingly enough, they were trying to also do basically this autoencoder or identity function. And they found that the certain training examples, not all, but certain training examples became attractors. They created essentially concave functions or compressed areas where they act like magnets in their specific pooling layer. And this meant that here that you can see the test image, and then they tried to do visual representations of that test image going through the network and how it ended up in a specific training image by the end. And that was a really interesting find to say, why is it that certain training examples are attractive to these downsampling? And why is it also that what we learned from Zhang Bengio et al., why is it that certain networks that are mid-sized learn edges, and small networks learn identity methods, and then large networks memorize? Why is that happening? Because we actually know from doing this at scale that these larger models, for example, the LLMs that we deal with today that are all overparameterized, and also overparameterized models in computer vision, we know that they actually generalize well. So why is it that they're memorizing, and what is happening basically? So in earlier machine learning, we usually would talk about this U curve where you have the test error, you're training, and if you give it a certain size and training iterations, you will at some point fit well. And then if you keep training or if you keep growing the network size, then you eventually overfit. But what happened is essentially in moving to bigger and bigger models, it found that if you keep training past this overfitting, you eventually generalize well again. What is happening? Well, it just so turns out that we don't actually need to, when we have these overparameterized networks, we don't need to think about overfitting. Why is that? Well, some additional research in this space that I think is very related is around margin theory. Okay, what are margins? Well, I want you to think back. We're dealing with hyperdimensional space and not space that we as humans can really make sense of. But I want you to move back to simpler space. So we're back in 2D here. And in 2D, we're going to imagine that the dots are in space. And we could imagine this in 3D, but I'm not very good at 3D drawing. And then we kind of want to make decisions between different groups of things. So maybe again, we're in computer vision and we want to decide, is there a cat in the photo? Is there a person in the photo? What is in the photo? And so we're trying to push these decision boundaries so that they're clean. So what we really want, and you'll know this if you ever studied support vector machines, is we want what we call a large margin. So we want to have the decision boundary to be between the different spaces, and we want the spaces to be as far apart as we can make them. And other research, this is from some Google research that's linked in the article, is that even in deep learning, so even in it's a non-2D space, it's not the same as a support vector machine, but even in deep learning, if we approximate these margins, so we can't calculate the margins, that's an intractable problem, but if we approximate the margins, so if we try to say like, how far am I from the decision boundary, and how far is the decision boundary from that other decision space, then actually if we track that, we know that the bigger the margins that are there at several layers in this deep learning network, that the better a chance that the model will generalize well and do well on unseen data. And when we combine then this margin theory with why is it that we're memorizing and we're still doing well, we can actually start to more deeply reason about what is being memorized, why it's being memorized, and how it's being memorized. These are still very open areas of research, so I'm not here to claim we fully understand anything. But one of the theories, again, going back to Feldman and Zhang's work, is that some of these memorization pockets help the model to perform well on other similar outliers. So just because something is an outlier doesn't mean it's not worth learning. And you can think about this too with things like in search algorithms. For a long time, we've purposely also accounted for things like spelling errors, especially common spelling errors, or things like multilingual input, where you have kind of a mixture of one language and then a random English word. Well, all in all, that's probably outliers, and yet it still represents things that the model will probably see. And even if we memorize those things, when the model then is asked to predict on something similar to that outlier, to that misspelling, to that erroneous input, then it will actually perform better and allow for both enough parameter space to generalize well on what it should learn and the extra parameter space to memorize what it might need to learn. And yeah, we'll leave it there. If you have comments, questions, feedback, please let me know. And I hope you're enjoying a cozy December or whenever you're watching this.